Welcome to the PhysicsPlace, the place to learn about physics, and in this video I'm going to explain how you can convert potential energy into kinetic energy and the other way around. And it has something to do with, for instance, falling rocks. They have a certain potential energy at the beginning, and at the end, when they're on the ground, they have no potential energy, but they do have kinetic energy. And also this rock, which is falling from this building, it will have a lot of potential energy here. Down here, it will not have any potential energy, but it will have a lot of kinetic energy, and in this video I'm going to explain how you can calculate those. So when something is falling, potential energy is converted into kinetic energy. So if the rock here and you will drop it from the building, then at the beginning the potential energy will be at the maximum because it has a very big height, and there will be no kinetic energy because it's in your hand and you will just drop it. So then the kinetic energy will become larger, but at the beginning there's no kinetic energy. So now you drop it and the rock will fall and it will hit the ground. When it hits the ground, there will be no more potential energy because it's already on the ground. The height is 0. But the kinetic energy will be at the maximum, so we just calculate just before it hits the ground. So all the potential energy has been converted into kinetic energy, and they're equal. So for instance, if this was 1000 joules, then here the kinetic energy will be 1000 joules. And then the energy went from having a certain height to having a certain velocity. It also works the other way around. If we have this person throwing a ball, then here there is no potential energy, and when throwing it you will give it a lot of kinetic energy. The kinetic energy will become less and less and less until it stops up here. When it's at the highest point, there is no more kinetic energy. It's stationary just for a fraction of a second, then it will fall down, but there's no kinetic energy here, and there's a lot of potential energy because it has a certain height. This meme also shows it very nicely. We have potential energy and we have kinetic energy. So first we have potential energy over here, and then in the middle the potential energy is being lowered and the kinetic energy is going up. So the potential energy is giving its energy to the kinetic energy, and then at the end you have no more potential energy and you have a lot of kinetic energy. And of course the other way around, when we are throwing something up, then we first have a lot of kinetic energy and then we have a lot of potential energy at the end. When there's no friction, you can use this equation. So we have the potential energy and that's equal to the kinetic energy. I already discussed it in separate videos how you can calculate them, and it will look like this. So the potential energy has this equation and the kinetic energy has this equation. And just short, the m, the mass, is in kilograms. The g is the gravitational acceleration. It's 9.8 meters per second squared, just 9.8. H here, the difference in height. And v, the velocity in meters per second, and the height of course is in meters. As you can see, there is a mass in both of the equations. So we have a mass here and we have a mass here. And usually when we drop something or when something goes up, the mass doesn't change. So we can divide both sides with the mass. So if we do that, then the mass here disappears, here it disappears, and it will look like this. So now actually the mass does not matter if something falls down. So if something falls down, it will have a certain velocity here and it will always be the same, and it doesn't matter what mass it is. This is of course only when there is no friction. When there will be friction, then it's not the case, but with no friction you can also use this one. So then we have the 9.8 here multiplied by the height equals a half multiplied by the velocity and of course the square. So an example, try this for yourself. Get a piece of paper, a pen and a calculator and try it if you can calculate this one. We have a cyclist with a mass of 85 kilograms on the top of a hill which is 26 meters. He rides down without pedaling, so he's not giving extra energy. It's just the energy he has because he has a certain height. Calculate the velocity at the bottom of the hill and you can neglect frictions. So the information we have his mass 85 kilograms, we have the height 26 meters, we have the g, which is 9.8 meters per second square. It's not given in the question here, but it's a constant here on Earth, so you should know that. And this is the equation we will use, because he will use his potential energy that will be completely used to get kinetic energy. So all the potential energy here at the beginning will be the same as the kinetic energy he will have at the end. This is the equation. We can use the mass because we have the mass. Of course, you can also just neglect this one because, as I just showed previously, the mass is equal in both. But I will now show it once with the mass. So all this information can be put in the equation. 85 kilograms here, 9.8 here, 26 because that was the height. Half is of course a half. The mass is again 85 kilograms, and the velocity here is unknown, and of course the square, don't forget the square. This is a number, this is also a number. You can use the calculator to calculate it. You will come up with these numbers, 21,658 and here 42.5. We divide this one and this one with 42.5, then it will look like this, and then we have still the square here, so we do the square root. and then we have a velocity of 22.6 meters per second, which is pretty fast for a bike, but that's probably to do with the fact that there is no friction. In reality there will be friction, so this velocity will go down because energy will be lost in friction. But for now, this is how the equation works. So this is how you can calculate from potential energy to kinetic energy. Now this one, now you throw a ball with a velocity of 54 km per hour upwards. Calculate the maximum height the ball will reach, and you can neglect resistance due to air. So now we have kinetic energy at the beginning, and it will get a certain amount of potential energy. We have a velocity at the beginning, 54 km per hour. It has to be meters per second, so we divide by 3.6, so it's 15 meters per second. We have the g, it's not given here, but of course we are on Earth, so this is a constant, 9.8. And that's it, that's all the information we have. We don't have the mass, we don't need the mass, because if we use this equation, this time it's the kinetic energy becoming the potential energy. We have the velocity, which is given here, the g, which is given here, and the h is the only one unknown, so we can now put in our information in the equation and we can solve it. So we have half multiplied by 15 and of course the square, don't forget square. We have 9.8 multiplied by h. So this is a number, and you will see that if you put it in your calculator it will be 112.5. We divide by 9.8, so the height will be 11.5 meters. So if you throw it with this speed, velocity, then the height will be 11.5 meters. There it will be stationary. Then of course it will go down again, then the potential energy will be converted into kinetic energy, and it will come back to you with exactly the same speed because there is no friction. Of course, when there would be friction, then the speed would be less, because then during the travel up and down energy will be lost into friction and then it will have a lower speed. But if there's no friction due to air, then the speed, or the velocity will be the same. This one is a little bit more difficult. A rock falls from a height of 50 meters. Calculate the velocity it has at a height of 30 meters. Neglect resistance due to air. So this one is a bit more difficult because we are not on the ground yet. We are still in the air. So the rock is still falling and we want to know the velocity on a certain height. And of course, then there still will be potential energy because it has a certain height, but already a part of the potential energy will be transformed or converted into kinetic energy, and we have to calculate which part that is and what the result will be in velocity because of that. So here is the velocity 0, and that's very important. It doesn't specify that, but it falls from there, so it starts with 0 and then it starts to get kinetic energy. So the potential energy here will be converted into kinetic energy, but not the complete potential energy. So not the whole 50 meters, because 30 meters before the ground we already want to know. So from 50 to 30, it's only 20 meters. So if we use this equation, we don't have the mass, then the height will be 20 meters, because it started at 50 and we want to know at 30, not at 0. So then the height is 20 meters. The acceleration due to gravity is 9.8 meters per second square. And the velocity we can now calculate. So we put it in, 9.8 multiplied by 20 equals a half, and then of course the velocity and the square here. Well, this is a number, 196. We divide by a half to get the velocity square singled out. Then we have 392, and then we have the square root. So the velocity will be 19.8 meters per second, and that will be somewhere here at a height of 30 meters. And then of course the rock will continue to fall. The velocity will continue to go up and the potential energy will continue to go down because the height will go down. But this is how you do it when you want to know the certain velocity at a certain height when it's not 0 yet. That's it. I hope you found this video helpful, and I hope you now know how you can convert potential energy into kinetic energy and the other way around, and that you now know that mass is not always important because they are in both equations, so you can delete them in both equations. If you found this helpful, please let me know by liking this video, and of course subscribe for more videos. Thanks for watching.